In this video, we will briefly explore exponential relations. So we're going to start off by looking at a little word problem. At the start of a cold, the bad bacteria in our body starts to grow and build up. Let's say the equation to model the number of bacteria, y, in hundreds, after x days is y equals 2 to the power of x. Day 0 is when you start noticing that you are sick. So let's start off by completing the table of values by subbing in each of the x values laid out for us to solve for y. So the first two I've already done for you. So I take this times 0 and plug it into my equation so that we do 2 to the power of 0. And you plug that into your calculator and you get 1. Then we do 2 to the power of 1, and that is 2. And if we continue, we'll do 2 to the power of 2, which is 4. 2 to the power of 3, which is 8, because that just means 2 times 2 times 2. And 2 to the power of 4, which is 16. And 2 to the power of 5, which is 32. So let's go ahead and take these values and plot the points. So 0, 1 is our first point. Then 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32. So this is what we have so far. Now, it tells us to calculate the first and the second differences. We're already comfortable and we know what those are. So the first differences, we're just taking our y values and subtracting them, bottom minus top. And if the first differences are constant, we know the relation is linear, but we can already see from our graph that it is not linear. And then our second differences, we're taking our first differences and subtracting them. And if they are constant, then it is quadratic. So let's get started. So for my first difference, I'm doing 2 minus 1, and that's 1. I do my next pair of 4 and 2. So 4 minus 2, which is 2. 8 minus 4, which is 4. 16 minus 8 is 8. And 32 minus 16 is 16. So those are not the same, so we know that it is not linear. Now for our second differences, we're going to take our first differences and subtract them. So 2 minus 1, which is 1. 4 minus 2, which is 2. 8 minus 4 is 4, and 16 minus 8 is 8. So these are not constant either, so it is not quadratic. Now the next thing we're going to do is calculate the ratios. So ratios should make you think of division. So we're going to go back to our y values, which I'm going to highlight right now. So 1, 2, 4, 8, 16, 32. And we're going to divide the y values, bottom minus top. So for my first pair here, 2 and 1, we have 2 divided by 1. Then our next pair is 4 and 2. 4 divided by 2 is 2. Our next pair is made up of 4 and 8. So bottom divided by top. 8 divided by 4 is 2. And then we continue with 16 and 8. 16 divided by 8 is 2. And then the last two, 32 divided by 16, which is also 2. So our ratios are the exact same. So we already said that because our first and second differences were not the same, it meant it was not linear or quadratic. But this new idea that the ratios are equal, then our relation is exponential. So for exponential, we have to do the division of the y values. And if we look at it graphically, you can see that it is increasing at a higher and higher rate as you go on. So it doesn't look like that quadratic where we had that nice step pattern. It is increasing exponentially here. Now, let's move on and see what would happen if our x values were negative. So when we look at our scenario, x equals 0 represents the present, and then the future is to the right of the y-axis, and the past would technically be to the left of the y-axis. So let's go ahead and just more for the mathematical part of it, let's see what happens if you have a negative exponent. So we already know that 2 to the power of 0 is 1. 2 to the power of negative 1 over here. If you plug it into your calculator, you get 0.5. And if we think of what 0.5 is as a fraction, it is a half. So for the next one, 2 to the power of negative 2, if you plug it into your calculator, it's 0.25. And that as a fraction is 1 over 4. Then 2 to the power of negative 3 is 0.125, which as a fraction is 1 over 8. So maybe you might see a pattern right now that these numbers in the denominator are the same as the original numbers in our table of values, 2, 4, 8. So you can kind of predict what the rest of it might be. So I want you to finish off the table of values and then come back to the video to check your work. So for negative 4, you should have 1 over 16. And for negative 5, 1 over 32 when you convert the decimal into its fraction. So now that we have these, let's plot the values on the left side. And these values are very small, so it's going to be hard to estimate, but we will do our best. So at negative 1, we were at a half, and then a quarter, then an eighth, a 16th, 1 over 32. So this gets closer and closer to the x-axis, but never actually touches it. And that is called an asymptote. So let's go ahead and look at C. As the y values continuously decrease, will the y value ever reach 0? Why not? No, it will not. Because there is no exponent you can apply in this situation to get 0. Because if you notice, all that the negative exponent is doing is making your fraction smaller and smaller. So if you look at 4, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4, 32 is 2 to the 5. All that negative exponent is taking the 2 to the power of and putting it in the denominator. And 1 divided by anything, as large as it is, will never actually give you 0. So no, because no exponent will give you 0. So because of that reason and the fact that it's never going to become 0 or it's never going to turn negative, we have an asymptote. So if we look up at our graph, our x-axis is an asymptote because on the left side here, your graph is approaching the x-axis, but it's never going to touch it or actually pass through it. Okay, so that's just a little word problem so that we can see what an exponential relation looks like. Now we're just going to review some grade 9 exponent rules. So you had 3 main rules in grade 9. The first is the product rule. If you have 2 terms with the same base, then you just add the exponents. So I take my m and n and add them up, and the base is staying the same. When I'm dividing, I'm going to subtract my exponents. And if I have an exponent to the power of another exponent, I'm just going to multiply those 2 exponents. So let's go ahead and try some examples. In our first one, we have 2 to the power of 2 times 2 to the power of 3. They have the same base, and because it's multiplication, we're going to add the exponents. So 2 plus 3 is 5. And now if we want, we can go ahead and evaluate this. So 2 to the power of 5 is 32. For the next one, we see it's multiplication again and the same base. If you don't see an exponent above a number, it's automatically a 1. So if I add 1 plus 4, we have a to the power of 5. For the next one, x to the power of 5 times x to the negative 1, I'm just going to add 5 plus negative 1 is 4. So x to the power of 4. Okay, try D and E on your own. And for E, just be careful that you're matching up the x's and y's appropriately. So go ahead and pause this video and then come back to check your work. So for D, we should just have y to the power of a plus b. And for e, we add the x exponents, so 5 plus 2 is 7, and the y exponents to get 13. Okay, for the next ones, we're doing our quotient rule, so we're dividing here. I have the same base of 3, so then I'll just subtract 7 minus 2, so 3 to the power of 5. And 3 to the power of 5 is equal to 243. For g, we're going to subtract 23 minus 14, and we get 9, so b to the power of 9. For z, remember there's an exponent of 1 on the second one, so 8 minus 1 is 7, so z to the power of 7. For I, we're going to match up the a's and the c's. So for the a's, we have 6 minus 2, which is 4, and for the c's, you're doing 2 subtract negative 1. So there's a double negative there, so you actually end up adding. So 2 plus 1 is 3, so c to the power of 3. So be careful with those double negatives, especially when there's a negative in the denominator. All right, for j, we're going to combine our product and quotient rule. So first thing I want to do is simplify my numerator by applying the product rule. So then for the d's, I'm doing 2 plus 1, which is 3, and for w, 8 plus 3, which is 11. And then I'm dividing by w to the power of 5, so I'm just going to focus on these two. So d to the power of 3 stays, and then w will be to the power of 11 minus 5, which is 6. All right, let's go on to our chain rule. So we have an exponent to the power of exponent. Your base of 7 will stay the same, and then 2 times 3 is 6. And if we do 7 to the power of 6, we get 117,649. Now for L, you have to apply this 4 to both the 5 and the 1 because it's x to the power of 1. So we have x to the power of 4 and y to the power of 20 because again we're multiplying those exponents. For m, you have to be careful to apply this 3 to the coefficient as well. So you're going to have 3 to the power of 3 because technically a coefficient has an exponent of 1 as well. And then a will be to the power of 9 times 3, which is 27. And then we can simplify our coefficient. 3 to the power of 3 is 27, and then a to the power of 27. Now for n and o, you do have an option here of when you want to deal with that exponent on the outside. I'm going to clean up inside as much as I can, and then I'll deal with that 4 at the end. So the 2 stays, but then p to the 3 divided by p to the 1, I'm going to subtract the exponents. 3 minus 1 is 2, and then raise it all to the power of 4. And just like with the previous example, remember the 2 has an exponent of 1 as well, so we're going to distribute that 4 into both exponents. So we're going to have 2 to the power of 4 and p to the power of 8 when we do the multiplication. And then 2 to the power of 4, we can clean that up and simplify it to 16, p to the 8. And then finally for o, we can simplify and subtract our exponents, so d minus c all to the a, and then you're multiplying your two exponents together. So you can either write it as a times d minus c, or you can do a times d minus a times c, like a mini little distribution. Either way would be perfectly fine. So all of these rules are from grade 9, so hopefully they are coming back to you. Now there are 2 rules that we're going to add on to for our grade 10 portion. So we're going to start off with our 0 rule, and then we're going to look at the negative exponent rule. All right, so for this first example, I just wanted to show you the layout of what I would like you to try. So for this 7 to the power of 4 divided by 7 to the power of 4. In the first column, I used the exponent rule. So I had division, so I subtracted. 4 minus 4 is 0. In the second one, I had the expanded form. So I expanded my numerator and my denominator using my knowledge that an exponent tells me how many times to multiply my base by. So 7 to the 4 means multiply 7 by itself 4 times, and I did that in my numerator and denominator. And if I simplify this, I notice that everything cancels out. This set of 7, the second set, the third, and the fourth. And anything divided by itself is just 1. So that's how I got this answer. So I'd like you to pause the video and try the second example on your own, and then we're going to try to make a conclusion about anything to the power of 0. So go ahead and pause and then come back. Okay, so hopefully you saw that again, when you simplified it, you got something to the power of 0. And because everything cancels out, we end up with 1. So that's our first rule. Anything to the power of 0, so let's say a to the power of 0 equals 1. No matter what it is, it could be the most complicated number as your base, but it is still 1 when it's raised to the power of 0. Now, let's see what happens with a negative exponent. So I'm going to fill the first one in with you. So if I use my exponent rule, 3 minus 4 is negative 1. Now let's see what happens when we deal with that. So I'm going to write my expanded form. My numerator will have 4 times 4 times 4. And in the denominator, I'm going to have 4 times. So then I notice that 1, 2, 3 sets of 4 cancel out, and I'm just left with a single 4 in the denominator. So I can write that as 1 over 4. Now let's try the next one. 3 minus 5 is negative 2. So now we're looking at, well, what if it's to the power of negative 2? So I have 4 3 times in the numerator, and then 5 times in the denominator. So again, 3 pairs of 4s cancel out, and then we're left with 2 4s on the bottom. So I can write this in two different ways. 1 over 4 squared, or 1 over 16, because 4 squared is 16. Now what I want you to start noticing is that here it was negative 1, here it was negative 2. The exponent on this 4 was 2, and on the exponent on the top one was 1. So pretty much, when we had a negative exponent, it turned positive when we took the reciprocal of that base, or when we moved it down into the denominator. Now let's just quickly try out this fraction example. So if I have 3 over 4, and I subtract 2 minus 4, I go to the power of negative 2. So let's go ahead and expand it. So I'm going to have 3 over 4 twice in the numerator, and then 4 times in the denominator. So that means that 2 pairs of the fractions will cancel out, so that I'm left with 1 over 3 over 4 squared. Now remember, when you divide, you're really multiplying by the reciprocal. So I can rewrite this as 1 times 4 over 3 squared. So our simplified answer is 4 over 3 all squared, or 16 over 9. And again, take a look at the exponent. Here it's negative, here it's positive, and the way it turned positive was by flipping that fraction. It used to be 3 over 4, but now it's 4 over 3. So for a negative exponent, we can turn it positive in two ways depending on what our base is. If our base is a nice whole number, or just a variable, then we can take the reciprocal, 1 over a, and now the exponent will be positive. Now I'm not raising 1 to the power of x, because 1 to the power of anything is still 1. So there we are. If I go to my next one, if I have a fraction as my base, I'm just going to take the reciprocal of the entire fraction. So instead of a over b, b over a. And the minute I do that flip, my exponent becomes positive. So I want to do two little examples before we go to the ones with the variables below. So let's say I have 5 to the power of negative 2. I can turn that negative exponent positive by putting the 5 in the denominator. So 1 over 5 squared. And if I evaluate that, that's just 1 over 25. Or let's say I have a fraction. 2 over 7 to the power of negative 2. I don't like negative exponents. So I'm going to take the reciprocal of my base, and now my exponent is positive. Notice that my exponent doesn't change besides the sign. It is just the base that is flipping. And now 7 squared is 49, and 2 squared is 4. So there we go, we dealt with the negative exponent. Now let's try some more examples with variables. So for the first one, we have x to the negative 1. I don't want that negative exponent, so I can rewrite this as 1 over x to the 1, which is just 1 over x. Let's try a to the negative 3. So I don't want the negative, so I'm going to take the reciprocal, and now that negative 3 is positive 3. And that's as far as we can go. With c, I have a fraction for the base, so I'm going to take the reciprocal, which is c over d. And then we can take this now positive exponent and put it into the numerator, so c to the 4, and the denominator, so d to the 4. Now I want you to pause the video and try d on your own. So you're using your grade 9 quotient rule, and then maybe you have to deal with a negative exponent. So go ahead. Okay. So if you use your quotient rule, 2 minus 7 is negative 5. And we're not happy with that. You are not allowed to leave your final answer with a negative exponent. So we can rewrite this as 1 over g to the power of 5. So really, when you're doing things and simplifying exponential expressions with multiple rules, you can do the rules in whatever order you'd like. I personally deal with the negatives at the very end. So let's look at e. I have a negative exponent there, but I'm going to worry about that at the end. For now, I'm just going to do my chain rule and distribute this negative 2 into the 2 terms in the brackets. Notice the 5 is outside the brackets. It is not affected by it. So I'm just going to write the 5. But x is now going to be to the power of negative 4, and y will be to the power of positive 6, because a negative times a negative is positive. Now, my only problem here is this. So this x to the negative 4, I'm going to put it in the denominator so that the exponent can become positive. The 5 and y to the 6, they're fine where they are. So my final answer will be 5y to the power of 6 all over x to the power of 4. And that's just the quick way of doing it. If you wanted to, you could have done this and taken the reciprocal on your own in the middle and then left the rest of them where they are. But that doesn't look right. So we know that any term is really over 1. So now you can see that 5 times 1 times y to the 6 becomes your numerator. And then 1 times x to the 4 times 1 is your denominator, which leads us here. But just taking that quick reciprocal and putting the term in the denominator is a lot more efficient. Okay, let's look at f. So for f, I'm going to apply that quotient rule. So for the x's, I'm doing negative 3 minus 2, which is negative 5. And for the y's, I'm doing 2 minus negative 5. I'm actually going to write that. 2 minus negative 5. So you have that double negative, which actually means addition. So it's y to the 7. I'm happy with where y to the 7 is, so I'll keep that up in the numerator. But I'm not happy with x to the negative 5. So x will go in the denominator and its exponent will turn positive with that swap. Let's look at g. I see a negative exponent on the outside, but I'm not worried about it just yet. I'm just going to clean up the insides. So first thing I'm going to do is clean up that numerator. So d will become d to the power of 3 because of 2 plus 1, and w will be to the power of 11. And then I can clean up the w to the 11 divided by w to the 5 by subtracting, so that I get w to the 6. And now I have that negative exponent. If I want, I can take the reciprocal of my entire base, or I can distribute the negative to it and then take the reciprocal. I'm going to take the reciprocal right now. So this is technically all over 1. So I'm going to rewrite this as 1 over d to the 3 w to the 6 all squared. And if I clean that up, it becomes d to the 6 w to the 12, when I apply my chain rule and do the multiplication. Okay, I want you to try this last one on your own, and then we'll take it up when you come back to the video. Okay, so first thing, let's clean up the x's. I see two x's together in my numerator, so those would become x to the 6. And then everything else stays as is. When I do my quotient rule, 6 minus 6 is 0, and 7 minus 8 is -1. Now I know anything to the power of 0 is 1. And then this negative exponent I'm not happy with, so it will go down into the denominator. So this should become 1 over y. And that's it. Now there's more practice on the next page for you to do, so I want you to try that out on your own and check your work with the solutions that are on the bottom of the page or the solutions online.